impact of the persistent oceanic noise sources on the coda of correlation wave fields. First, it doesn't work actually. How can I change? Okay. So for the motivation, actually, most of the seismologists monitoring try to use the common strategy, coda interferometry, and the main assumption is that mostly they contain the scatter wave fields. So actually, I'm going to show some of the result that is not actually true. So I have a very short review for some basic information for some of the audience might not familiar with that about the ambient seismic noise interferometry and originates of the ambient seismic noise and coda of correlation wave fields. And then I go through to the data preparation and results. So actually, seismic interferometry allows seismologists to replace the source with seismic stations. So with correlation observation, we can retrieve the approximate green functions between different stations as we consider one of them as a source. So with we need the perfect noise. That means coming from the isotropic and uniform noise source distributions. By this way, we can retrieve the symmetric correlation function contained the travel path between the two stations in causal and causal parts. So the main contributions of the direct arrivals come on from the virtual source and station by this technique. So about the ambient seismic noise originates, we have two main origin or category. One of them regarding the lower than 1 Hertz and causes by actually natural loading causes. And there are, for example, some storms in the lakes and ocean swells can generate this kind of the noise sources. And there are two main well-known peak frequency. One of them is related to the primary microsize that create by the coupling oceanic wave energy into the sea floor as the wave approach the shallow water. And the other, the secondary microsize that is the vertical pressure creating that two seismic waves traveling in the different directions and actually creates this kind of the noise. And the other main category is related to the lower than greater than 1 Hertz and is related to the anthropogenic sources. In this study, we want to focus on the actually this category about the natural loading causes in the lower than 1 Hertz. So we know we observe the considerable asymmetry in amplitude and spectral content. That means that we have both difference in source process and also distance to the sources in the direction radially away from the stations. So actually, with the presence of the non-uniform noise sources, we observed the coda in the later part of the correlation wave fields, and actually the coda of the correlation wave fields give us the opportunity for many monitoring application as the coda travel in different paths and so contain the scatter wave fields and also multiply scatter physical arrivals. And they also consider as a powerful method rather than some ballistics monitoring that are so stable for example, some measurements. So in this actually study, we want to focus on the coda of the correlation wave fields and to investigate some basic assumption in this way. So we try to answer this question, does the coda wave field show complete scattering, and does the persistent noise source influence the coda of the correlation wave field, for example, in this case, the oceanic sources? And also in this way, are there any seasonality variation impacts regarding the stability of the coda of correlation wave fields? So we need to actually retrieve the correlation functions. In the data preparations, we actually consider the seismic station in Greifenberg array that includes 13 seismic stations in Germany. And we select some master station as a virtual sources in different back azimuth and distance. So we actually retrieve the reference correlation between each master stations and each stations of the Greifenberg array. This is the showcase of the reference correlation between each master station and, for example, GRA1 in our seismic array. So we focus on the actually primary and secondary microsize frequency range, and the time resolution is 2 years, and we retrieve the 2 hours correlation wave field as actually outlined by Benson et al. In 2007. After that, we need to see the main contributions of the, for example, wave fields for example, different directions. We use the seismic array beamforming. Most of us are familiar with this method. Actually, this is the phase match algorithm, can allow us, for example, to detect and extract the coherent wave field contributions to the recordings or to the signals. We use the classic planar beamforming method, but on the pre-computed correlation wave fields. So by this way, for example, this is again the showcase of the reference signal between the BRMO and GRA1. So we are applying this technique on the, for example, in the case of the BRMO, 13 reference stations from the master stations and also seismic station in Riefenberg array. So we use the or apply the beamforming, and this is the results of the beam power in each sliding window throughout the signals. We see the result for the slowness and back azimuths. So in this plot show us the 3 distinct arrivals. 2 distinct arrivals can be related to the direct arrivals. Actually, the Rayleigh waves with the slowness range 3 seconds per kilometer coming from to the master station in a causal and away from the master station in causal parts. This is exactly we expect in the seismic interferometry. But however, about the later part. The later part of the correlation wave field show the distinct directions in the, for example, mostly in the direction of the 320 until 360. And we can interpret as a direct and repetitive Rayleigh waves that comes from the direction of the north and northwest of the seismic array. This direction can be related to one of the well-known, actually, oceanic noise sources regarding the macrosystem at North Atlantic Ocean in our region of the study. So at the first look, it seems that yes, later part of the coda can there are some impact from the oceanic noise sources, but we want to investigate in more details in each type of wave type, including to the correlation wave fields. So for a more accurate process, we applying the 10-minute windowing function first for each, for example, wave type wave fields in the correlations. And we label us based on the, for example, wave type, direct arrivals for the ballistic waves, and then the later part just labeled as a position, early and mid and end coda. And then we use a beamforming method in each window individually. And then we show actually the average of all the beam power we retrieved in the grid search of the slowness and back azimuth, not just the maximum value. So I show you first the result for the primary macrosystems. This is the 10-minute window regarding to the direct arrival. As we can see, is exactly the same for the previous slide. And the most coherency of the wave field is related to the masters and receivers in the polar plot. And also the radially parameters show the slowness, and also we can see azimuth and geometry of the both stations, but the ray triangle. But when I go to the coda parts, we can see the most coherency comes from the direction, again, from the north and northwest of the Riefenberg array. So might be we just say that, okay, it's similar to the directions of the BRMO, north and north, for example, west in this way. Where is my mouse? Okay. So we just try to the another master station with completely different geometry. I'll show you the result for the OJC in the Poland, and we can see also the direct arrival and orientation of the back azimuth change based on the path between the masters and also receivers in the acausal and causal part. But in the actually later part of the correlation wave field, still we see the actually most coherency comes from the same direction, from the North Atlantic Oceans. So in the primary microsites, we see considerable coherency in the later part in these directions. So we just need to verify with the main contributions of the wave field on the raw data, just focusing on the 13 stations in the Greffenberg array. So this is show the applying the beamforming on the just raw continuous data in the same time resolution on 13 station in Greffenberg array. And we see there are agreement between the results of the raw data beamforming and also correlation beamforming in the primary frequency range, primary microsize frequency range. So in the next steps, we want to see that if we assume actually the oceanic noise sources impact the coda of the correlation wave fields, we must see the actually algorithm or pattern of the seasonality variation on the coda, because we know that the oceanic waves are so seasonal. So in this part, we want to answer or check this question. And as we know, the seasonality variation are more stronger in the secondary frequency band. So I'll show you the result for the secondary frequency band in this way. So first, I just have a short review about the general global pattern for the seasonality variation in the secondary frequency band. Regarding the winter time, we know the stronger secondary microsite sources in the northern hemisphere is related to the southern tip of the Greenland and North Atlantic Oceans, regarding, for example, the Europe region study. And however, about the summer times, actually, most of the studies showed we have very distant sources from the southern hemisphere. Actually, these are a very high apparent velocity attribute as a P waves that generated by some strong ocean activities during the northern summer in southern hemisphere. This is a general pattern or algorithmal seasonality variations during the summer and winter for the secondary frequency band. So I just first of all show you the results of the seasonality for the raw data beamforming on the Greffenberg array. On just 13 station in Greffenberg array, this is the result of the beamforming during the winter months. And as we can see, we have the considerable contributions from the actually direction of the North Atlantic Oceans that attribute as a remote secondary microsize originating from the North Atlantic Ocean in our study area. And also in some part, we have some coherency from the north direction that some study attribute as a local secondary microsize in shallow water of the North Sea. So, and also the slowness range is related to the surface waves, is similar to most of the studies. And also about the summertime, we can see beamforming or most coherency is related to the slowness range lower than 0.1, and also can be attributed as a P waves from created by some distant sources regarding to the Greffenberg array. In this way, we are familiar with the seasonality variation in our study area, and in the next part, I want to investigate the seasonality variations of the coda of correlation beamforming. So in the first part, I just retrieved the reference correlation for 6 months regarding the winter time, and then, for example, this is the result for the BRMO. And we somehow see some messy pattern for the secondary frequency range, and we can expect that because of the attenuation in this frequency range for the surface waves, and also some complex wave propagation in this frequency range. But we still see the most coherency for the direct variable is related again to the master station and receiver, regardless for example, winter, summer, or yearly. And also we have most coherency from the same direction and same slowness range regarding the North Atlantic Ocean and in the surface phase slowness range. When we focus on the summertime, they just retrieve 6 months reference correlation during the durations of the summer. We see again for the direct arrival is a stable results, but however the coda, the story is different. Actually, most of the time is dominated later part by the high apparent velocity and the slowness range of the 0.1 during the summertime. In this slide, I can show you the directions of the wave field. We just can see the slowness distributions in the polar plot. So I show you the direction by this plot. Actually, we know that the actually high wave, oceanic wave is related to the oceanic activity. So for example, the average height oceanic wave is a maximum from the southern hemisphere during the summer. And we see in this polar plot, the maximum wind power is distributed in the direction of the south and with a slowness range of the body waves. And also regarding the winter, the high oceanic waves is related to the North Atlantic oceans, and also the distributions of the maximum wind power is related to this slowness range and the same directions. So this is kind of show you the directions of the wave coming from. So by this wave, coda wave correlation wave field is not completely scattered. And regarding the imprints of some persistent oceanic noise sources in the secondary and frequency band, we see that we can observe in the, for example, 2 hours correlation wave fields in the later part, the imprints of these strong sources. And also regarding the secondary macrosize, a strong seasonal variation observed during summer and winter, and based on the oceanic activity.